The what?
The light, that be too bright. That's how you did that, but
Yeah, I think it's, I mean, you can see, but it's a little bit of an effort, right?
but,
For some reason, this isn't going between.
oh,
This is fine.
this is fine.
And also, this microphone is very sensitive. Like I'm talking now, and it's broadcast.
That's a roof.
Yeah, that's the microphone for in here. Shouldn't be able to pick up too much. Like, just,
Can't you hear? You hear?
not to the speakers.
Yeah, yeah.
Wait, what?
Well, I'm just saying that I'm talking and it's picking up my voice, so it's a crazy sensitive microphone.
This mic?
Yeah.
No. That's good. The question answer session will also get recorded nicely then. I'll have to come and do this.
So you have Fab at...
Yes. Yes. In fact, Fab was something which was already there. There is a colleague who set it up about I think 5 years before I joined there. I mean, that's when they started. So we have a Wraith, E-line.
That's what we have also.
Yeah, and then there's a general purpose evaporator, but I have my own evaporator next to my lab. No, it's actually a partially home built system. So at Berkeley we had something, we got it designed, essentially it's the vacuum part, right? So we got this, what's that company, HPC or, I'm forgetting the name, one of these HPD vacuum or something.
Oh, yeah, yeah.
These guys, so there was a design from NIST, from Joe Amantado's group, which we adapted at Berkeley. Dan Slichter was the one who sort of took a lead on that. And it's basically a 2-chamber system with a rotating stage and pumped with, so then a standard CTI cryo pump. The Plusies uses a different philosophy. They don't use cryo pumps, they use turbo pumps and liquid nitrogen traps. So I again...
Ours is a cryo pump.
Okay. So we got
You can do whatever you want.
Yeah, I see. Oh, you have a Plusies but with a cryo pump.
Well, Mike has one.
Yeah.
We just bought one for the general purpose clean room.
Okay.
And both have cryo pumps, I believe.
Yeah. So the general purpose one we have is also a cryo pumped one, but it's a single chamber system. It's one of those bell jar type designs.
I
Where
may be wrong. He may have a turbo.
he doesn't have cryo pump, Michael.
Yes,
Yeah.
but the general purpose one will have a cryo pump.
Okay. So yeah, so then we got, there was a vacuum company in India. They're actually quite good. They even sell all over the world. So we got the vacuum systems designed from them. So they were quite good. So they took my design and then they said, okay, look, this is the same thing. We have a simpler stuff which we know how to make well. And they came up with a new design. They integrated the E-beam source and the cryo pump and everything into the design. And it works great. You know, the qubits have decent coherence time. So that's the main thing. Sorry? Yeah, I got it. These guys had it, yeah. Yeah. Feeling all right?
Maybe.
You're not going to like collapse in the middle of
No, I
it?
basically went back to my office and slept until when you last saw me.
Okay, that's good. These flus can be terrible.
Yeah. So everything you're showing today is on silicon, right?
Yeah, we made one sapphire qubit just for testing. Everything is silicon. Only the good stuff.
I do like your logo. It's kind of crazy.
Yeah, I had a previous version which I told you one of my students, he's an artist. So.
Michelle came up and told me he liked my logo without me prompting him. He told me he thought the font choice was appropriate. It was one of those moments where you're like, I've succeeded as a person. And then the other way of thinking about that is Michelle has warped me so deep that I automatically pick the right font.
Yeah, these things run deep. I see myself objecting to things which I was like, I'm making sure. Right.
give it a couple moments. Just everybody's late. I thought we were all sitting down in the lab.
No, I called you, but for some
I don't have
reason
cell
you
phone
never.
reception in that lab.
Oh,
We're too far underground.
ah.
I didn't realize that I was supposed to bring.
It's fine. I just thought you'd walk by, so it's okay. We can move.
We take the elevator.
So what's the one up there on the top? So top right, I guess, is your site, is your department at TIFR?
No, these are both government departments which give funding.
I see. So this is like the NSF equivalent.
Yeah, this is Department of Atomic Energy.
Oh.
They are
Is
our-
it like France where they give a lot of basic research?
They are our primary funding source. I have a fellowship from these guys.
Like, because it's in the CNRS, the nuclear thing in France?
CEA.
Or CEA, right?
They don't give money.
I thought they,
A little bit.
I thought they gave positions, no?
Positions, yeah.
Huh?
They employ people.
Yeah. But for basic science or just nuclear?
Yeah, basic. All.
Yeah, Rick Perry. Former Texas Indian cheerleaders in charge of DOE now. Okay, should we start? So today I'm very happy to introduce to you. Okay, so I'm gonna try the full name first, and we'll fall back on what we actually call him. This is Rajamani Vijayaraghavan. Yeah, we call him VJ because that's what he says to call him. He publishes under our VJ, so the other name won't help you that much. VJ and I kind of swapped past each other. He came to Berkeley short before I left to go back to Yale, to work, sort of switch labs. While he was at Yale as a graduate student, he was at a lot of the sort of birth of circuit QED. He invented on accident the first parametric amplifier, although he didn't realize that for like 5 more years. So there goes a lot of head start. When he was at Berkeley, he did realize it was a parametric amplifier, did the first measurement of superconducting quantum jumps, did a lot of stuff on quantum measurement, magnetometry, cool qubits, basic quantum science. Now he is at the TIFR in Mumbai, right?
Yeah.
On the beach. I don't know, I hear it's nice, I haven't been yet. Where he runs his new lab, which is it called Q plus Mac or just QMac?
It's a QMAC, yeah.
All right.
All right. Thanks a lot, Michael, for the introduction and for inviting me here. It's a pleasure to be here. It's my first time visiting Pittsburgh. I wanted to come and see how Michael was doing, and you guys have been doing some interesting stuff at the Quantum Institute, hiring a lot of new people. So yeah, it's good to be here. I joined TIFR about 4 years ago from Berkeley, and I'm going to be telling you something about what we've been doing more recently with some new kind of qubit systems. And this work was mostly done by graduate students, Tanay Roy and Suman Kundu, who are the 2 senior grad students in my group, and several other people here. Most of these guys are short-term students who come for some projects or a 1-year sort of research project program, and they've moved on to other things. And that's currently my group. I have a postdoc, 3 students, and a scientific staff, and a couple of project students visiting. So as I said, I'm going to be telling you about a new sort of, not really new, it's just a different way of thinking about multi-qubit systems. So I will sort of do a very quick introduction. This is an expert audience, but I thought I'll just, re-motivate you with some standard slides about quantum information. But the bulk of my talk is going to be describing this new device, which we call the Trimon. We like to name things in this community, and Michael is actually a big expert on coming up with nice names. And in fact, he objected to the first name we had when I sent him a draft. And then eventually had to change the name. But yeah, Michelle objected too, so we had to change the name. So, and then I will sort of tell you towards the end. Huh?
What was the rejected?
It was triconium. It was an attempt at the other kind of names of qubits, which end with NIUM, and also to bring in a little bit of Indian flavor to it, because tricone or tricone, as it's said in Sanskrit, is a triangle. And it's a 3-spin system, sort of in a triangle lattice. So we said we will be clever and do this, till Michelle pointed out that, oh, the NIUMs are actually reserved for a specific kind of qubit.
You mean all the ones invented by Michelle?
No, it's about things with, this difference between internal degrees of freedom and plasma degrees of freedom. So I had to agree that this qubit was more the MON type and not the NIUM type. So we changed the name before we send the paper out. So I'll then sort of towards the end tell you a little bit of where we are taking this idea and what kind of things we think we can do with this kind of stuff. And if I have time, I'll flash a couple of slides on other projects we are doing in our group. Okay, so everybody knows stuff here. Basic idea of quantum information is that you want to have quantum two-level systems to encode your two-level states. Unlike classical bits, you can create superpositions, and in a convenient way of representing these things is on the Bloch sphere. So you have your north pole and the south pole representing the eigenstates, and then any other point is your superposition states. And sort of the simplest and mostly not very useful way of describing why quantum information is potentially powerful is that if you have a register of n classical bits, you can only put it in one of the 2 to the n combinations. But with the n qubit register, you can create a superposition state, which is a superposition of all the 2 to the n states. And then essentially a quantum algorithm is something which manipulates this gigantic Hilbert space at the same time. And that, if you do correctly, you can do interesting things. And that's sort of the simplest way of motivating where using quantum bits can actually buy you some power. And there are some standard examples of the kind of problems. Again, you must be familiar that finding prime factors. So if we take 2 prime numbers and I give you the product and I say, tell me which 2 prime numbers are multiplied, the reverse problem is very hard. And the time and the complexity grows exponentially with the size of the problem. And this is sort of also is at the heart of various encryption techniques. And I see someone is like nodding their head. And Peter Shor invented an algorithm in 1994 where he showed that if you had a quantum system and you could program it and run the algorithm, you can actually change the complexity class of this problem. This is sort of an essential feature, is that it completely changes. It's not really about speed of computation in terms of like a processor or a clock cycle or anything like that, but it really changes the complexity class of the problem from exponential to polynomial. So if you have a very large number, the time to solve such a problem can come down dramatically and become tractable. There's another one which was also reasonably famous called Grover's search algorithm, but there the improvement is only from scaling as n to square root of n. And I think these 2 algorithms sort of really started the push for developing actual physical systems to make these devices to implement quantum states and store and process quantum information. The other part, which I think a lot of physicists are excited about, is what's called quantum simulations. And this again comes from the fact that if you're trying to do a full quantum mechanical calculation on a classical computer, it soon becomes intractable in terms of the amount of resources and processing power you need. Of course, a lot of efforts have gone into developing specialized techniques for solving many-body problems, and they're very successful. But if you're trying to sort of brute force solve Schrodinger equation on a many-body system, it soon gets out of control. And Feynman, in fact, way back had pointed out that you should just use a quantum system to solve for another quantum system. And here the idea is that from the information perspective, any quantum 2-level system is identical in terms of its ability to store and process information. So you have some physical system you want to study, but it's intractable maybe experimentally. But if you have another set of controlled 2-level systems which you can manipulate and interact nicely, you can make it mimic the behavior of the system you're interested in. So essentially simulate one type of quantum system which is hard to work with another type which you are actually designing and controlling. So with this in mind, there are some very basic requirements you need in order to implement a hardware which would actually do this. You need some choice of quantum 2-level system. You need the ability to create arbitrary states for the single qubit so that you can prepare all kinds of superpositions in a nice way. You also need to be able to measure these quantum states quite efficiently. And then you also finally need to couple these systems together so that you can go from single qubit operations to multi-qubit operations. And then, of course, this kind of coupling has to be extended to larger and larger number of qubits, and there are various ways of doing that. And there are sort of primary challenge always has been that these quantum systems have finite quantum coherence, which basically means that they don't survive for too long, and different systems have different time scales. And then this second point, scaling to large number of qubits, is still pretty much an unsolved problem. There are many different architectures. People are trying various different ideas, and whether one can, how to scale it in a way that things don't get too complicated. A lot of efforts have been made to come up with new ideas for scaling, and there is a lot of work going on this. But these are sort of the two major obstacles. Quantum coherence has been improving. The time scales have been improving steadily over the last 10, 15 years, and we still probably need to keep pushing that. But you also need to come up with ways to scale them so that you can actually build a reasonable size processor which can do things which a classical computer cannot do. And as you already know, there are a whole host of systems which people are working on. The early experiments on sort of isolating individual quantum systems came from the trapped ions. The 2012 Nobel Prize was basically a reflection of that, developing those techniques. There's NV centers in Diamond, which is work going on here in Pittsburgh as well. There are quantum dots on 2D electron gas systems. And what I'm going to be talking about is superconducting circuits, which are essentially macroscopic electrical circuits, sort of more macroscopic than these systems in terms of their size scale. They are very highly tunable because you can design them the way you want. You can put control knobs on them and even have in situ coupling. The size scale of this system also means that they are very easy to couple. In fact, there are many systems, for example, the NV centers, which have now demonstrated single qubit operations, but it's very hard to create coupling. And there are other examples of that because it's really a conflicting requirement. If you isolate your system very nicely, they become very nice and behave quantum mechanically, but then to create interactions becomes a challenge. But having strong coupling can also be a drawback because it would also couple to things you don't want it to couple to, for example, the environment. And this was a big question. In fact, several years ago, I would have a question mark on this coherence slides, this bullet point here, and because it wasn't clear whether these macroscopic systems can have sufficient coherence before they they can actually be useful. But there has been really no fundamental roadblock we have encountered, and it's just really about ensuring that the relevant degree of freedom of your macroscopic system is very well protected from the environment, and you can turn that coupling on and off, and that would really allow you to push the coherence. So there's been steady progress, tremendous progress in this thing. Scalable, and I've sort of started putting a question mark on this because in the early days, superconducting qubits were always pitched as the most scalable of all designs. And this basically stemmed from the fact that, hey, these are microfabricated circuits, and they are just like other integrated circuits which we already know how to do. So once we figure out how to do a few of them nicely, we can scale up to a very large system quite easily. I mean, from the fabrication point of view, today in most labs, you can make thousands of qubits, and with a very good chance that all 1,000 qubits work with decent coherence. But it's not really clear yet, and there are many ideas out there, how to actually arrange those 1,000 qubits in an architecture which is easy to control and manipulate, and so on and so forth. So this is question mark in the sense that this is yet to be demonstrated in a robust way. Okay, so I'm going to then shift to introducing the the most famous and successful superconducting qubit, which is also called the transmon qubit, which is nothing but an anharmonic oscillator. And that's really, I think, the simplest way to think about it. It consists of a Josephson junction shunted with a capacitor. The Josephson junction can be thought of as a nonlinear, non-dissipative inductor, and once you shunt it with a capacitor, it forms an anharmonic oscillator. So instead of a harmonic oscillator, you now have a cosine potential, and the quantized energy levels are no longer equally spaced, and that allows you to isolate the two lowest levels of the system and create an effective quantum two-level system. There are higher levels, and they do play a role in many cases, but we can, because there is sufficient difference between these two, you can use frequency selectivity to address just those two levels. And here's, for example, an image of a device which is made in a lab. This is what is called the 3D transmon. It's 3D because the capacitor, essentially the fields are mostly in vacuum, and they come from these two big almost millimeter-sized paddles here, and the capacitance is between these two parallels, and right in the middle is the two Josephson junctions in a superconducting loop. I forgot to mention that by threading a flux through this loop, you can tune the inductance, and hence you can tune the transition frequency of these qubits. And essentially, you also need to operate at very low temperatures so that you can prepare the system in the ground state. And typically, we work with microwave frequencies which have equivalent temperature of few hundred millikelvin. So going to a dilution fridge at 10 millikelvin allows you to sort of robustly prepare the system in the ground state, even though there are caveats there. But you don't want too much thermal energy to be scrambling, like creating a mixed state here. So that's important. There are, of course, reasons for going to low temperatures because one uses aluminum. These devices are all aluminum devices which have a TC of around 1 Kelvin, and you want to be sufficiently below that transition temperature to not have quasi-particles which can give rise to dissipation. So the superconductivity helps in developing low loss components so that these oscillators, in the classical sense, they can ring for a very long time. And that's equivalent to saying that this excited state will have a large lifetime. And the Josephson junction gives you the nonlinearity which you need in a nice way. Okay. So to measure these systems, we put such a chip. So here in the middle, you're seeing a silicon chip with the device made on it inside a copper cavity, or it could be also an aluminum cavity. And this cavity serves several purposes. It, first of all, acts like a nice sample box. It protects the qubit from radiation and other sources of noises. But mostly, this cavity also has an electromagnetic mode, which is basically just the TE101 mode, and is defined by the size of the hole which is milled into this copper block. And that couples to this qubit and creates what we call a cavity QED kind of system. And essentially, when the state of the qubit changes, it shifts the effective frequency of this circuit, and that can be probed in a resonance measurements. And to actually do a measurement, so here are sort of two resonant curves shown for the ground and the excited states, and you sort of bias here and look for a phase shift which is different between the two states. And that's essentially how you measure the state of the qubit, and you also use the same ports here which allow you to couple power into these cavities, and you use the microwaves for preparing the states by sending signals at the transition frequency of the qubit, and you do measurements by sending a signal at the cavity, close to the cavity resonant frequency. Okay. And the real nice thing about superconducting qubits is that it's kind of like a little game of Lego. You have three fundamental elements: a capacitor, a Josephson junction, and an inductor. And by combining them in different ways, you can actually create, in some sense, a designer Hamiltonian. So this is sort of a generic sketch from this review paper which came out a few years back. And basically, there's a whole bunch of qubit designs which have come about in the last 10 to 15 years with various interesting names. And the transmon qubit, the one I just showed you, is right here. The two axes basically tell you the ratio of the capacitance to the Josephson inductance and the ratio of the linear inductance to the Josephson inductance. The transmon did not have a linear inductance, but there are other qubit designs which do use. So you're flexible, you have the flexibility to use this. And they all, this is sort of like a little periodic table of artificial atoms. It's what like we to think about. And you have these control knobs, except that you design these. These are not given to you by nature. You choose where you want to lie on this. And different points along this have different sensitivities to different sources of control and noise. And the transmon has been sort of the most successful in terms of being the simplest qubit design, which is very robust, has less sensitivity to design fluctuations, and is protected from charge noise, which is also one of the biggest problems, and gives you good coherence time. So it rapidly spread to most labs soon after it was invented. In fact, most quantum operations have actually been done on this kind of a qubit only. But the point is that you can really make anything you want, and that's really one of the flexibilities of that. So now coming to this question of coupling the qubits together, well, how do you make these qubit interacts? So I already told you that these are, you can think of these as oscillators. So we have all studied, pendulums. And you have also often probably seen this coupled pendulum experiment where you put two pendulums on the same wire, and then you can set one of them in motion, and if they are on resonance, you do this transferring of energy back and forth. It's a very similar idea here. You can couple these two oscillators just by putting them next to each other and putting them with capacitances. And then if these two oscillators have the same frequency, they will exchange energy back and forth. And this creates a joint evolution of the 2-qubit system. Okay? And this kind of coupling can be done in several ways, not just capacitors. You can use capacitive coupling, which will give you nearest neighbor. So you can couple this device to that device, and then this device could be coupled to another device over there. Or you could also use resonators for what we call long distance coupling, there by using a resonant mode and getting the qubits to interact with different parts, which is an extended object, so you can actually create coupling for non-nearest neighbors by connecting appropriate resonator bus between the qubits as well. And these two have been used quite successfully in many qubit designs. The essential features are that these inverse what's called transverse coupling or dipolar coupling. The qubits are usually off resonant. So normally this qubit and this qubit will be at different frequencies so that they don't keep exchanging energy when you don't want them to exchange. And you turn the couplings on and off by either tuning the frequencies and bringing them into resonance for a particular amount of time, or you use RF tones to create effective coupling even though they are off resonance. So in the dressed basis, they develop an effective coupling. So this allows you to turn the couplings on and off. And this is a nice way of creating coupled systems. A few examples of very successful designs using this kind of an idea. Here is a 9-qubit processor from the Martinez group at UCSB and now Google. These X's you're seeing, each of them is a transmon qubit, and they are arranged in a linear array. Each of them has a little readout cavity. These are now the 2D versions, which are microfabricated on a chip, as opposed to the 3D cavity version I have showed. And they have control lines coming in. And these have nearest neighbor capacitive coupling, and they were able to demonstrate various nice things. This has sort of become a workhorse of their of the lab, and they have done various kinds of proof of principle demonstrations using this.
Why are we seeing a bunch of bright dots?
These?
Yeah.
Oh, they're actually just the edges. What these are is just a meandering resonator. It's just the image.
Same for the others?
No.
Here?
Some of that stuff,
Besides,
some of those bright dots you're seeing are crossovers. Like you see.
Oh, these things, yes. These things are actually crossovers for the coplanar waveguide line, which is coming in to do the control and stuff. Yeah. And these are all input feed lines, and they go around like this, and they come here. There are feed lines out here. So these bright dots are essentially little crossovers from one side of the ground plane to another side of the ground plane. It's just a technical detail. So the ground planes are here, and when they narrow down, you have to keep the two grounds at the same potential. That's very important for the coplanar waveguide to guide the waves without creating its own resonance. Otherwise, these two ground planes tend to become at different potentials, and then you can actually create spurious resonances. So there is actually a lot of engineering which goes into making sure that these kind of modes are not excited. Okay. So this is the example of the nearest neighbor capacitor kind of coupling. Here is another chip from the Waldorf group where the qubits, the transmon qubits, are these 4 boxes here, and they are now connected with this meandering kind of section, which is the resonator bus. So now this resonator allows you to couple this qubit to that qubit, this qubit to this qubit, and so they have made it in a square lattice kind of geometry. And again, this allows you to create couplings and run quantum algorithms. A similar version from the IBM group is shown here. This is a 5-qubit system. Oh, no, this is actually an image of a 4-qubit system. Here are the 4 qubits, and there are all these squiggly lines, which are the resonator buses, which are coupling the different qubits. And a version of this is actually now on the cloud, as it has been for a year. You can sign up for this, and you can actually draw little algorithms on their interface, and you can either get it to be solved by a classical computer, which is perfectly fine for a 5-qubit system, or you can actually run it on their machine, and it will spit out the result, and you can look at it. And surprisingly, a lot of people are actually using this and writing papers on running various algorithms. Though not much can be done on a 5-qubit quantum processor, which you cannot do on a classical computer. But it's sort of a proof of principle demonstration of where the technology is. Okay. So to now contrast this from something I'm going to be discussing for the rest of the talk, back in the day, the earliest demonstrations of algorithms was actually done in NMR. And NMR systems had a very different model for a coupled qubit. First of all, you had to identify the right molecule, which would give you several qubits. And in fact, I went back to this paper where they first demonstrated Shor's factoring algorithm in 2001 in an NMR system, which had 7 qubits, and with pairwise longitudinal, which means sigma z kind of coupling. Okay? This is essentially a complex molecule where the numbers sort of tell you where the location of the spins are, and the interactions in the molecule sort of gives you this form of coupling, and this table is actually showing you the resonance frequencies. These are actually detunings from some control variables, some control signals, not the actual resonant frequencies. And these are all the couplings between all the spins. Essentially, every spin is coupled to every other spin in the system with a certain magnitude of coupling, and essentially the coupling terms are of this type, sigma z, sigma z. Now, even though the early demonstrations came from NMR, NMR is now no longer considered a viable, scalable technology for building quantum computers. Is because you have to, first of all, it's really ineffective. It's a pseudo qubit. You're working on an ensemble, which is mostly in a thermal state, and then you have a very small sort of component of this which you play around and manipulate with. But it was a good platform for people to sort of work on these ideas and develop protocols and things like that. And it becomes harder and harder to identify systems which would have more qubits in them, and then to be able to manipulate them in a controlled fashion. So the question is, what if you could design this kind of an NMR type of molecule using superconducting circuits, but in a way you like it, rather than looking for it, even though I think chemists actually worked on designing a special molecule which had the right properties. And that's essentially sort of the kind of system I'm going to be talking about. So here I introduce this new 3-qubit circuit. Now let's just pay attention to the circuit very closely. It has 4 Josephson junctions in a loop, and I'm sure many of you have seen this circuit. In fact, Michael's lab uses this kind of a ring structure to make amplifiers. It's exactly the same ring. And we have sort of shown a generic circuit here where each node is connected to every other node capacitively. So there's these capacitances CC, which are the capacitances which are shunting each junctions. And then there is a capacitance CA from this node to this node. So that's this capacitor here. And then there's a capacitor CB, which connects this node to this node. In practice, we can make this in this 3D transmon design by making 4 junctions in a loop like this and connecting them to now 4 paddles instead of 2 paddles like we had in the transmon. So basically now there are capacitances between these paddles and those paddles, and they all represent these things. So you can see from the symmetry of the device that the neighboring capacitances will be identical, mostly. But this capacitance here is going to be larger than this capacitance, and that's intentional. And so that basically introduces a difference between CA and CB. And the way you think about this circuit now is, instead of the transmon, which is 1 anharmonic oscillator, this is 3 coupled anharmonic oscillators. If you now solve for this circuit, you will get 3 normal modes. Each of those normal modes is nonlinear and hence behaves like a transmon qubit. And they're all coupled to each other, so there's always a coupling. And you'll see the kind of coupling one gets.
Sorry,
yeah.
So maybe I'm counting wrong, but is there one degenerate mode?
So the 4th mode is not very useful. So basically he's saying there are actually 4 junctions, and you can kind of see 4 oscillators here. But because of the constraint that they're connected in a loop, one of them is just a breathing mode where all the nodes are just going up and down. So that actually doesn't couple to any of these, and it actually will not be a mode in the system unless you start thinking about the capacitances of this node to a distant ground plane. So that mode we always ignore. In general, you're right that if I have 4 junctions with some capacitances, you will get 4 normal modes. Here you only have 3. So you'll always get n minus 1. That's just a feature of this particular kind of circuit. The normal modes of this structure are actually easy to sort of imagine, especially when all the 4 junctions are considered to be identical. Okay? And the modes are defined like this. There is what we call the A mode, which is a dipolar mode. So you just think of this, these 4 things as inductors, and you say, well, I'm going to just look at this as an effective inductor, which is there are 2 in series, another 2 in series. It looks like 1 effective inductor, and now that is shunted by some effective capacitance, so it's going to oscillate back and forth between these 2. So these are the modes of oscillation. There is an identical mode, but which is rotated by 90 degrees, which is this one, which is just the same thing, but now the oscillation is between these 2 nodes. So this is now just an inductor in the orthogonal direction. And the point of this image here is that this is now representing the cavity in which the system is going to be placed, whose resonant mode has electric fields pointing in this direction. So this is basically the property of the TE101 mode. And when you place this device inside this cavity, only this dipole is aligned to the electromagnetic field, and only that actually couples to the mode. So this dipolar mode, ideally speaking, is decoupled from the cavity. And then there is a quadrupolar mode where these 2 oscillate together, and these 2 with respect to these 2. So sort of geometric we want to see, it's this ring structure. There's one more dipolar mode which goes like this, another dipolar mode which goes like this, and the quadrupolar mode sort of goes like that. A little bit later, I'll present a different way of looking at these modes, which will sort of be more intuitive. For a simple circuit like this, it's sort of easy to identify. But once you do that, then you define these, by using these symmetries, you define these so-called mode variables, which are the correct normal mode coordinates for describing the system. So you have this phi A, which is just the difference between phi 1 and phi 3, which is the flux on this, which we call the node fluxes, essentially just the integral of the voltage at that particular node. So it's phi 1 minus phi 3. It's natural because it's plus and minus like that. This one is phi 2 minus phi 4. And then this one has a combination of all the 4. It's phi 1 plus phi 3 minus phi 2 minus phi 4. And so that's once you define it, and then you just write down the Hamiltonian, because you know how to write down the Hamiltonian of each individual junction. In this new normal coordinate, this Hamiltonian takes this very special form. And again, many of you must have seen this in Michael's talks, because this is the same Hamiltonian. The difference is that in the amplifier work, you want to use this term. Whereas in this work, we actually set the flux, which is this phi is the magnetic flux through this loop. We set that to 0, and that gets rid of this term completely. And we actually use this part of the Hamiltonian for implementing 3 coupled qubits. And how does that come about? You now take this Hamiltonian, you now add the capacitive parts, which is basically the charging energy part of this circuit, and then you just expand this to quartic order in all the mode variables. Okay? So you will get a q square term, a phi square term. This is the harmonic part, and then the first nonlinear part for each mode is just a phi to the 4th term that just comes from expanding the cosine up to the 4th order. So this again now just looks like the same anharmonic oscillator. So this mode is now a transmon-like qubit. It has the same kinds of properties. You do the same for the other 2 modes, you get exactly the same structure. So this is also a transmon-like qubit. This is also a transmon-like qubit. By transmon-like, I mean weakly anharmonic oscillator. Okay? But the interesting part comes from the fact that when you now expand to quartic order and look at other combination of terms, you get these terms phi A square, phi B square, phi B square, phi C square, and phi C square, phi C square.
Hey, Vijay?
Yeah.
The quartic term, you have 2 96s and 6.
Yeah, this is just because of the way the definitions have an extra factor of 2.
So
This is
so one of the qubits doesn't have a much higher anharmonicity than the other?
no, it doesn't. It goes back because of you have to make sure that the choice of conjugate variables is correct. So that's basically what gives rise. In the end, the anharmonicities are quite similar. Okay. So these phi A square, phi B square can be compared to the phi A to the power 4th. So you see, this often is called the self-Kerr term. This is nothing but the cross-Kerr. This tells you that if I put more excitation in the same mode, it's going to become more nonlinear, and it's actually the frequency is going to come down. And here it's saying that if I put excitation in the other qubit, that's going to affect the mode structure of the first qubit itself. So that's the pairwise coupling. When you quantize this circuit now, you sort of write down these in terms of the raising and lowering operators, and then you specialize to a spin half system. That is what gives rise to this sigma z coupling. Okay? And so in that language, you have 3 spins with 3 different frequencies, and they are basically can be chosen by choosing the Josephson junctions and the capacitance structures. You can place them several hundred megahertz apart, along with this pairwise sigma z coupling, which we call longitudinal coupling. And then this part is the interaction with the cavity. The surprising part here is that even though there was only one dipole which was aligned with the cavity, you actually get that every qubit, even the ones which are uncoupled from the cavity, do exert what we call a dispersive shift. It actually shifts the frequency of the cavity as well. And that actually comes indirectly because of this sigma z term. I'll explain later a little bit more the origin of that. Now, what does this kind of a coupling buy you? I'm going to now specialize to a 2-qubit subspace so that we can see this more clearly, and then later on we'll see what happens in the full 3-qubit. So the 2-qubit, you have 2 qubits here, and then one pairwise coupling, sigma z. So here's now is the level diagram. You have to think of it in the 2-qubit subspace, 0, 0, 1, 0, 0, 1, and 1, 0. Now if I look at this transition here, which takes 0, 0 to 1, 0, the way you want to think about it is that addressing this transition will cause rotation on the first qubit when the second qubit is in 0. And you compare that with this transition. This transition also changes the state of the first qubit, but only when the second qubit is in 1. So these transitions are no longer specific to individual qubit. They're actually addressing the joint states of this multi-qubit system. And this difference is between this transition and that transition is exactly the coupling 2J, which we have introduced here. Okay? This is what the always on coupling buys you. But what this means is that if I now apply any rotation on this, it is a conditional rotation. It's a rotation which depends on the state of the other qubit. And specifically, if I do a pi pulse, which is basically flips the state of the qubit, that is what is called a control NOT gate. And the control NOT gate is a very key element of a universal set of gates for doing basically quantum manipulations and quantum algorithms. So here in this 2-qubit subspace, the control NOT becomes a very trivial operation. It's just the Rabi rotation between these 2 levels. You have 4 levels to address, but that's what it is. But you pay a price, which is that now single qubit rotations are slightly more non-trivial, in the sense that if I want to only rotate or change the state of one qubit independent of the state of the other qubit, I now have to address 2 transitions, because I need to invert or change the population corresponding to the 2 other possibilities the other qubit can exist in. So in general, if you now think about a larger system, so for a 2-qubit system, single qubit rotations need 2 rotations or 2 frequencies. For a 3-qubit system, it's going to be 2 to the 2, which are the 4 possibilities of the other 2 qubits. You will need 4 rotations. So this kind of inverts the complexity. Multi-qubit gates become very easy. Single qubit gates become slightly more complicated. Okay. So the measurement, as I was telling you earlier, there is a dispersive shift which comes actually from all the 3 modes. This mode, which is the coupled mode, exerts the conventional dispersive shift from the Jaynes-Cumming Hamiltonian, and that expression looks like this. This is just for reference. So what happens there is that you have your qubit detuned from your cavity, and there are 2 different cavity frequencies for the 2 different qubit states, and that's basically the dispersive shift, and that's how you detect the state. Now when you introduce this, look at the second qubit, which is the B qubit, which is the uncoupled qubit, it's actually not coupled to the cavity at all. So it doesn't actually directly affect it. But when this qubit changes state, you have 2 possible frequencies for the coupled qubit. This is because of the sigma z coupling. So it changes the frequency of this qubit, and because this qubit is coupled to the cavity, it's now pushing the cavity a little bit. And that is the indirect source of the dispersive shift. So now, similarly for the 3rd qubit as well. So it's the sigma z coupling allows you to measure the uncoupled qubits because of its coupling via it. But there is a very nice feature here, is that because it's not directly coupled, there is no decay mode, ideally speaking, via the cavity. Normally we protect that by keeping the qubit far away from the cavity so that it doesn't decay into the environment strongly. But in this case, you have actually separated these 2 functions. The coupling to the cavity has become independent of how strong the signal you can do. And I'll comment on that a little bit towards the end. Okay. So because these are now joint states, you have to now think of even the measurements in the joint basis, because you're now measuring the joint property of, say, the 2 qubits in this particular case. So the typical setup involves your qubit plus cavity. We send it through a low noise parametric amplifier, and then you demodulate and digitize to basically get what we call measurement histograms. So here are some sample histograms of the 4 basis states. Okay? You have to think of the x-axis as just a proxy for the phase shift which I was showing you, which you will get when the qubits are changing states. So the 0, 0 state has a histogram here. So the width of this histogram is just sort of the noise in your system. And then the 1, 1 is way out here, but 1, 0 and 0, 1 are kind of overlapping, which means that I cannot separate 1, 0 from 0, 1 in this picture, but I can nicely separate 1, 1, 0, 0, and both of them from this particular thing.
Why do they look separate?
These two?
The red and
Oh, they're slightly separated. They're not exactly, they're not fully
How
separated.
can you measure them separately?
Oh, because these are individual measurements. So this is taken by first preparing it in 0, 0, measuring the histogram, then preparing it in 0, 1, measuring the histogram. So these are 4. What I'm saying is that if I was able to do it in one shot, then I won't be able to distinguish between these two possibilities.
Look at the bumps at the bottom. You see there's this contamination from the proper preparation.
Yeah, those are, of course, there because of relaxation and improper preparation as well. Right now, I'm just talking about the separability of these histograms. So what we actually do, because in order to really fully understand the state, you have to be able to distinguish all the 4 possibilities. So in one measurement, we distinguish this from this block from this one. And then we can actually apply these control knots to interchange 1, 0 with 1, 1 and 0, 1 with 0, 0. So in a second measurement, we are able to now get the full information. So you can get the full, what we call the ZZ operator measurement, which gives you the populations of the relative 4. And now to do a full quantum state measurement, you have to apply 3 rotations on all these qubits so that you're measuring along all the 3 axes, and then you can reconstruct the density matrix of your full 2 qubit system. Okay? So here are some numbers from a sample. So the 3 modes, you can see the frequency separation is typically about 5 to 600 megahertz between the different modes. This is the anharmonicity, which tells you the difference between the 0, 1 and 1, 2 transition. That again is quite nice. And then these are the couplings, which is the coupling between the 3 qubits. And then here are the coherence number. The relaxation times are typically between 30 and 50 microseconds, which is quite good. And these are the Ramsey echo times, which tells you about low frequency dephasing, basically dephasing noise in your system. So these are comparable to typical transmon qubits. So we haven't really deteriorated the quality of these devices by making it a more complex circuit. So you have sufficient anharmonicity, strong coupling, coherence is good. Okay, so now we can start preparing some states. Because the C0 is such an easy thing to do here, you can do a Bell state preparation quite simply. You start with 0, 0, you apply a pi/2 rotation on one of the qubits. Now it's just a single pulse because you already know what the initial state of the qubit is. That keeps the second qubit in 0, but creates an equal superposition of the first qubit. And then you apply this control knot, which takes it into this kind of a Bell state. Then we do the full quantum state tomography of that. And here are the density matrices, the real and the imaginary part. The solid curves are the experimental data, and the outlined ones are the one what you would expect for the proper Bell state of this type. And you basically do an overlap fidelity of the expected state to the tomographically reconstructed state, which is done using a maximum likelihood estimate, and you get a nice sort of high fidelity of about 96%. You can now combine these C0s and do what is called a swap operation. This consists of 3 C0s, AB, BA, and AB, and that allows you to flip the quantum states of the any two states you store on the 2 qubits. You can interchange the states of that. So we created a state of this type. We created an equal superposition on the second qubit and this kind of a superposition state on the first qubit, and that's the density matrix after preparing this and before this swap operation, which is reconstructed with a fidelity of 97. And after the swap operation, you get a slightly reduced fidelity because you lost some in the gate. But these are small numbers, so we're just basically telling you this is fairly good quality of control and manipulation you have on preparing these states. Again, the solid ones are the experimental data, and the outlines are the expected stuff. And that's just the imaginary part of the same density matrix. Okay. So now we want to move to the full 3-qubit state. So far what we did was we didn't touch the 3rd qubit, we just left it in the ground state so that we can do the manipulations. But there was another reason we couldn't do the 3-qubit experiments in the first set of experiments we did. And this has actually got to do with the power coupling problem. So remember I told you these other 2 qubits are not coupled to the cavity? And we send our microwave power through the cavity. So it actually was very hard to excite these modes. We had to put in a lot of power. And if this was a perfect system where these junctions were identical and all the capacitors were identical and my chip was aligned perfectly to the correct axis, I would never be able to excite this system. But of course, there's always a little bit of asymmetry. And in fact, we wanted to now introduce intentional asymmetry because we were not able to drive this. And what that did was that when we were trying to drive the B and the C mode, we were coupling a lot of power to the A mode. And even though they were off resonant, they're sufficiently strong that they cause frequency shifts and AC stark shift effects. So then you have to calibrate those effects out and it becomes a real mess. You have to calibrate some 48 parameters to, you still, ultimately if you want really good quality gates, you still have to do that. But by introducing a little bit of asymmetry, which means that we now made these junctions intentionally different in size, in somewhat of a controlled way. There's always fabrication uncertainty, but we introduce additional ones on top of that. And essentially the way to think about it is that now all the 3 modes are mixed. The new modes are superpositions of the old modes. So which means that every qubit mode now has a little bit of dipolar component, which is basically the red one. So now the coupling to the cavity is increased. I can manipulate and drive them a lot more easily. And here we made a device again. And these are the numbers. Again, the frequencies are separated by 5 to about 800 megahertz. Then harmonicities are quite good. The coherence times really didn't deteriorate, even though we introduced some asymmetry. And the echo times were not so great as the previous one, but this I think was for a different reason. One thing, if you noted that the coupling numbers have fallen while the harmonicities have increased, and this is actually a feature. As you make these more and more asymmetrics, the coupling actually drops. But here, we have sufficient coupling to still address the individual transitions. So here's now the full 3-level qubit diagram. There are 8 basis states, as you would expect for a 3-qubit system, and then there are 12 transition frequencies which you have to address. So now the generalized single transition is a controlled control knot because it now depends on the state of the 2 other qubits. A 2-qubit C knot will now require 2 such control knots, and a single qubit rotation will require 4 such control knots. So clearly, a system like this, if I want to say make a 10-qubit system with this kind of couplings, it's not really the way to go because you will have 2 to the 9 different frequencies you have to address for each single qubit rotation. But for a small number of qubits like 3, this is completely manageable with the same hardware you need for doing conventional qubits. And the reason is that the couplings are a few hundred megahertz. The frequencies are all clustered together around one frequency with a few hundred megahertz. You can use a single generator for each qubit, just like you would do otherwise, and use simple modulation techniques to create these extra sidebands which you need. And you can even create them simultaneously if you want, and address all the 4 transitions at the same time, rather than, as I've shown here, one after the other as well. There are some pros and cons of doing that, but it is possible to do it. Okay. So here's now how the 3-qubit joint measurement looks like. So now you have 8 basis states, and here are the histograms of all those 8 states. Now you can see that you cannot separate many combinations, but by applying the same kind of technique and now doing more successive measurements, you can interchange these populations with the distinguishable ones and actually reconstruct the full density matrix by just adding more measurements to your tomography anyway is an ensemble measurement, so it doesn't really make much of a difference in the overhead you need to distinguish these states. Okay. And then of course you do the full tomography, you have to do all the pre-rotations, you measure along all the 27 basis states, use the same maximum likelihood estimates. So we went ahead, and this is fairly new stuff. We only got it a couple of months ago. We now can make basically what's called a GHZ state. You go from 0, 0, 0, and you apply a pi by 2. You create a superposition on the first qubit. Then you do a control knot to take it to a Bell state. And then with the 3rd qubit still in 0, and then another control knot, which basically now gives you the GHZ state.
So why is it 27 pre-rotation?
Sorry?
On the last line.
Oh, it's like 3 times 3 times 3. So 1 pre-rotation is no rotation as well.
Yeah, but I thought it was like 4 cubed minus
4.
1. Because the I.
Oh yeah. That is, I'm not counting that here.
Oh.
Yeah. So this allows you to create the GSD state, and this control node is also called the Toffoli gate, which is a very, again, sort of an important gate to be done. And here are the reconstructed density matrices. Here is the real part of the density matrix. Again, the solid ones are experiment, the outlines are the expected ones. And the fidelity is about 89%. It's not as high as the previous one. And in fact, we are a bit surprised because we actually didn't expect this to be, we were expecting it to be a little bit lower because the coherence times were comparable and the pulse times were also comparable. And the main reason for this actually turned out to be a different problem, and I'll just tell you about that in a second. This was the original level diagram I showed you, but remember that these transmons are actually weakly anharmonic oscillators. They don't just have 2 levels, they have higher levels as well. So there are these 2-level excitations of the individual qubits, and sometimes they come very close to 2-level excitations which are distributed amongst 2 qubits. So when you're trying to address a particular transition in this subspace, you actually, if another transition or level is very close by, you will leak out of your subspace, and then that cannot be distinguished in the measurement, so you make an error in your tomography. So what we actually think here is that the quality of the GSD state is actually very good. But when we do the tomography and we move the states around all over the place, we actually get a bad result. So what we need to do now is to tune the parameters so that we can move these levels sufficiently far away from this. And that's possible to do by playing around with the device structure. So you need to tune these device parameters. And I'm going to quickly tell you a technique which is sort of adapted from previous work done at Yale and at Sherbrooke of what's called black body quantization. The problem is sort of a generic problem that I have n nodes and they are connected by Josephson junctions and capacitors. I need to find out how to write down the Hamiltonian for such a system. In the most general case where these junctions need not be equal, the capacitances need not be equal. And essentially the idea is to first linearize the problem and think of this as a coupled oscillator problem, and you can solve for the normal mode analysis. So I'm just going to quickly cycle through this without explaining too much. This is fairly standard stuff. You write down the generic capacitance matrix and you write down the generic Josephson matrix for all of these things. You first, and then you construct your Lagrangian of the system. Then you, expanding it to the second order basically gives you the coupled harmonic oscillator problem. You first find the eigenvalues and eigenvectors of the capacitance matrix. You construct this new matrix, which is basically normalized by the eigenvectors organized by the eigenvalue, and then you transform the EJ matrix based on this new C tilde matrix to basically, it's like a double simultaneous diagonalization. And the eigenvalues and eigenvectors of this new matrix, EJ matrix, gives you the frequencies of the modes, and the eigenvectors basically give you the mode structure. This is basically the structure of how the modes are oscillating. So if you go back to the 4-junction case, we saw that phi A was phi 1 minus phi 3. You can now sort of unwrap this ring into a linear chain with periodic boundary conditions, so the 1 and the 1 are repeated, and you get these kind of mode structures. If you sort of now connect these dots, you can now start to see a structure. It's basically, they're like Fourier modes of a discrete ring. So that gives you an intuition of how to think about these kind of modes. And then you can solve, of course, do this calculation numerically for any parameters. These modes won't look that nice when the junctions are not identical. They will get all mixed up, but that's fine. You can do the calculation. You can now start thinking about how to take this further. Well, if I have more junctions in the loop, then here's the highest frequency mode where every node is alternating back and forth. Then you have 2 next lower frequency modes which are 90-degree phase shifted. Now these peaks and zeros don't necessarily line up at the node position, but that's okay. You can still calculate them. And then so you have, this one has 5 normal modes, and again they give rise to 5 qubits. And then you want to now finally add in the nonlinearity. After you have computed the new mode structure, you plug it back into your nonlinear part of your Hamiltonian, which is basically the potential, and then you expand them after quantizing it to and compute the self curve, which gives you the anharmonicity, and the cross curve, which gives you the coupling. So you then get basically, for this case, a 5-spin system with all-to-all sigma z coupling, and you can sort of extend that from there. So very quickly, I will now tell you about what we are thinking of using these systems for. One is just to actually use this 3-qubit system, but use one of the protected modes as sort of a good single qubit, because it's isolated from the environment. At the same time, you can still measure it. So these conflicting requirements are nicely solved. So here's an example from a device where this is the coupled mode and this is the uncoupled mode. So there's a fairly large difference in coherence times. And then we are trying to now optimize these to give you very good separation between these measurement histograms. So here we have 98.6% fidelity in separating the ground and the excited state. So we're trying to optimize the design parameters. There are other proposals and previous experiments which people have done with a slightly different kind of a coupled qubit system to optimize this. And so that's one direction. So here it's a 3-qubit system, but we're only using one of the qubits as a nice single qubit for doing experiments. We're also thinking of this 3-qubit system as a nice building block for doing error correction. And error correction is essentially the idea that you want to encode your single qubit state onto multiple qubits to sort of build in some kind of redundancy, but you use quantum entanglement to protect the system from errors. In the case of the 3-qubit bit flip code, you only can protect against one type of error, which is a bit flip. That is, you can, if one of the qubits flips from its 0 to 1, so you get 4 possibilities: no error, error on first qubit, error on second qubit, and error on third qubit. So the protocol has to distinguish between these 4 possibilities, and you can now construct measurements which only look for the difference between these four cases and doesn't really try to project in these eigenbases. So the state doesn't get destroyed when you measure it, but you can detect the error, and then when you know which particular error has happened, you can flip the state back. So that's sort of the generic idea of error correction. You measure the error, not the state, and for that you have to engineer these parity measurements. To do this kind of encoding from a general single qubit state to a general 3-qubit state, the Toffoli gate is sort of very natural, so it fits in quite nicely into these things. So we are trying to do some parity measurements with these kind of 3-qubit building blocks. As I already mentioned, we actually made this device for fun because, as I said, that it's going to be very difficult to control a 5-qubit system, though it's not unimaginable because, for example, the NMR experiment was a 7-qubit system of this type. So here's an example of such a device. It just looks the same. Now you have 6 junctions in a ring, and you have 6 capacitor pads. And here are the numbers, the 5 frequencies, the coherence times. They're not as good. It's just some preliminary results. And the anharmonicities look similar to transmon qubits. So they do work like qubits. We also were able to measure all the couplings between every pair of spins. So this is now a 5-spin system with each one coupled to every other was. And you can see that there's fairly strong coupling between these things. So this is something we've been playing around with. Another direction is to use, again, these 3-qubit units as effective single qubits, but the single qubit excitation can live in any of these modes. And here the idea is that if you had 2 of these next to each other and the excitation actually lived along the dipolar mode and the dipoles are aligned, they will couple to each other strongly. But if the excitation was living in the orthogonal mode, then they will not couple to each other strongly. And you can do the same thing with the quadrupolar mode. So here one idea is that can you change the coupling between 2 systems by changing the mode in which these qubit excitations live. And this was actually originally motivated from similar capabilities in cold atom systems. I visited a lab many years ago where you have these atoms trapped in an optical lattice, and then normally they're not talking to each other, but they're able to now selectively excite. I need to find some antinode here, or a node. They're able to selectively excite their atoms into a large Rydberg state, and they develop a large dipole moment. And then you can create selective interactions. So one can imagine doing something like that where you have an array of these systems, and you can have like a protected mode and a coupled mode, and you can bring those selectively out and maybe create interactions between them. So you can probably create spin chains, and you can turn the couplings on and off by just changing which mode the excitation resides in. Okay. And a more sort of standard scaling, which is actually done for single qubits already, is to now use a bus cavity to couple these trimons together. The point here being is that I have a very nicely controlled 3-qubit system where I can probably do these gates with very high quality. And now I use the standard dipolar coupling between such 3-qubit units to scale up to a larger number of qubits with reduced complexity but higher quality of gates. So we think that this might be a way, this is still very preliminary idea, we have to figure out how to actually do these gates in an efficient way between these things. But it looks like it might be possible to build a smaller scale processor, maybe, so this would, for example, would be a 12-qubit system where we can create probably gates with higher cavity. Each one will have its readout cavity so that we can do joint measurements in 3-qubit units and a bus cavity for coupling these qubits together. So that's basically what I wanted to say. So I hope I have convinced you that this Trimon is a nice 3-qubit system which has strong longitudinal coupling. The coherence times are good and we have good single and multi-qubit control, and it also has these protected modes which can be handy for several applications. I showed you how to do these high fidelity CNOT and Toffoli gates, and there seems to be potential for scaling this up for quantum computing applications, but at the same time quantum simulations. There's still open ideas here because we're trying to figure out now that we have this technique now to analyze these complicated systems. Is it possible to engineer the kind of couplings you would like to see in a specific spin chain by combining these devices in the right way to develop an intuition for building the kind of Hamiltonian you might want to study? So these are some of the things. So that's basically it, and I just wanted to flash some of the other topics we are working on. Since I'm not too much over the time, I'll quickly flash some other work we have been doing. This came out a little over a year ago, where we developed a very simple technique for improving these parametric amplifiers, which are very important for these quantum measurements. They essentially are your first stage amplifiers, and we improved the bandwidth of these systems. In fact, the kind of systems Michael and I worked on at Berkeley, they had about 30 to 40 megahertz of bandwidth, and by just adding the appropriate impedance transformer, the chip is actually exactly the same, the way we're making. We figured out the right way to make this impedance transformer to get the bandwidth up to 600 megahertz or so in this particular device while maintaining good noise performance. So these will be handy when you're trying to measure multi-qubit systems with multiple cavities which are frequency multiplexed, and that's a direction we are trying to work on. And very recently we started playing around with these nanomechanical resonators made out of graphene. So this is actually a device made in our lab. What you're seeing here is the center conductor of one of these CPW resonators, and then you have a graphene flake sort of wrapped around, which forms a capacitive connection between the center conductor and the outside conductor. This is exactly the kind of system the group of Gary Steele developed at Delft, and we are doing this in collaboration with a colleague who works with graphene devices in our institute. And we are actually interested in looking at different quantum measurement and back action regimes for these kind of systems, especially if we make the cavities, the microwave cavities, nonlinear. So this is another experiment we're working on. We also are interested in doing weak measurements. So we have some preliminary results where we can do weak measurements and then look at the back action. And this is the kind of stuff Michael did at Yale using the JPC. And basically, yeah, that's all I wanted to say. So I'll just flash this slide and take questions.
The new beard.
Yes.
Becoming a club.
Yeah.
So it seems as though you're always sort of outnumbered in terms of the number of degrees of freedom of your device and the cavity in which it's being coupled. Is there, so if you wanted to scale to 5 and
You're commenting on this?
Well, I don't know. I mean, the bus cavity, I guess, it wasn't clear how that addresses all of this. But
Oh, so this particular technique is something which is already being done, except it's being done with single transmons. So each of these are 1 qubits. So what you're seeing is just a different layout. I mean, I'm again imagining this in the 3D architecture. This is the standard cavity, which is used to measure this qubit. So in our case, this will give you a joint readout of the 3 qubit, which is this block. And each one of those will do the same. This common bus cavity is just a way to create couplings between any of these pairs of qubits. The resonant frequency of this cavity is not such a critical feature. It's just a way of creating virtual couplings between, couplings using virtual transitions in this particular qubit. There are various protocols there's something called the resonator-induced phase gate, where you drive this resonator, this bus cavity, at the right frequency, and that creates couplings between the modes. So the idea here would be that these dipolar modes will be slightly different in frequency, so that when no photons are present in the bus cavity, no couplings are turned on. And then you can turn on the coupling by driving this bus cavity appropriately. So again, this idea at present, I mentioned in the beginning, in the dressed picture, you will get some coupling which can be turned on and off.
But at that point, you've been coupled 2 at a time, right? I mean, can you do parallel gates?
You mean between
Like
all
you
the
have
4?
10 of these, and you want to couple 1 and 3, and 2 and 7, and 4 and 8.
I think it should, I mean, you mean to say do them at the same time?
Yeah, because if you have to do them in sequence, then you're going to run out of coherence.
Oh, sure.
So I guess what I'm just saying, like, just generally, it seems like the number of cavity modes isn't scaling as aggressively as the number of local modes, and that you're always going to run into some problems.
Okay. I mean, there are, clearly no sort of solved prescriptions of how to keep pushing this forward. Of course, in this kind of geometry, if you restrict yourself to doing the couplings between 2 units at a time, then you can actually do it. But then there are, for example, completely different ways of looking at. There's something called the surface code architecture, which has a very different method for scaling to multiple qubits and things like that.
So you would do surface code with or pentamons?
We are not thinking in that direction, but if you have the couplings between the right set, because the surface code is a 2D fabric, where you have couplings between each to the next 4, and then they operate by doing local operations and then measurements. You only need like entangling gates between certain pairs, and then a sequence of measurements. The reason the surface code is being followed by a few groups is that it seems to have the lowest error threshold to actually build, but it's you have to take that with a pinch of salt. So it has the lowest barrier of entry. So you can tolerate more errors in your gates, and it can still work, but then the price you pay is that you need a larger and larger fabric, the worse your individual qubits are, to create one logical qubit, which is sort of fully error corrected.
Yeah, I think the thing that's not clear from this is that you get one gate at a time at arbitrary range. Whereas if we replaced it with neighbor-to-neighbor coupling, then all the easy couplings would be neighbor-to-neighbor. But then when you need the arbitrary range one, then that would take
You have to keep going through in the linear chain. Here, there is no difference between, even though physically this looks closer, but these are all effectively the same distance in some sense. So you can create any coupling. And what we are imagining is that, I now have this 3-qubit block, which is basically very nicely controllable, and then I can now extend this to a system like this. And this particular architecture has already been demonstrated for single qubits. So for the same complexity, you can go to scale up to 12 qubits without having to have many more of these and a lot more control.
So you've shown the red ones here talking to the bus.
Yeah.
But won't they all 12 talk to the bus?
No.
Won't they all 3 talk to the bus? They all 3 have a dispersive shift to the bus resonator, right?
To this resonator?
Yeah.
Yeah.
Yeah. So is it only the red ones that you could do a gate on, or is it any of them?
No, the way, at least the initial idea is that you can go between these different modes using the 3-qubit control, but you will want to do gates between only the dipolar modes. But in principle, you should be able to do it because there's dispersive shift. That's right. Yeah.
I guess what I'm wondering is, can you bump up the number of cavity modes that you can work with?
Oh, you don't, maybe I'm not understanding your question exactly. There is only one cavity mode
Yeah, he's saying
here.
add more. He wants a higher connected graph.
Yeah.
The cavities themselves have several normal modes, but maybe I'm not.
Well, ones that are accessible that are, can be tuned.
He wants like a bus that couples the nearest 6, then a bus that couples the nearest 2, and a bus that couples the nearest 4.
I see. So you want to be able to create multi-qubit operations in one go, rather than doing them one at a time. Yeah, I think, I mean, in principle it should be possible, but I don't think there are any such proposals for many body interactions
Well, I don't know.
at the same time.
In the CSS code, it's not really clear like what some of those bigger codes assume about your various couplings, right?
Right.
But at least, so we have the sort of the dumbed down version, which is just an infinite point of qubit, which is the surface code, which is only neighbor to neighbor. And then we have like the 3-qubit code, the 5-qubit code, the 7-qubit code, the 9-qubit code, and then we have like Dairy Dragons. So the thing you're talking about could be perfect in some kind of code, but we don't know it or its extensibility, so we don't have a good reason to jump on it, if that makes sense. I guess I think the worst thing would be if you invest a lot of time and money into some architecture that only works for 132 qubits, but you don't know how to go to 256 qubits. That's why everyone's jumping on the surface codes, because you can just tell your funding agent, you give me infinite money, I'll put infinite qubits in the plane, you do what you want.
Right. I mean, and there are different philosophies on this. Like the Yale group now has a very different philosophy that, oh, we're just not going to go this way. We're going to create a very different kind of a qubit, which is error correctable without scaling up. So here you have to scale up at least to a reasonable size before error correction can be demonstrated. They're working in a completely different way by saying, well, we're going to make a good logical qubit first, and then scale up to create gates. And
But at least in principle, according to Mike and Ike, if you have 2-qubit gates, that's enough. Right?
Yeah. But the problem is that how many operations and how they're going to fight with coherence. So this will be a constant.
Well, as long as that overhead's not exponential.
Yeah. Yeah.
So you mentioned you apply external field to get rid of sign turning, right?
Yeah.
So, like, how do you know that turn is cancelled in a play?
Oh, so you can monitor the properties of the device, for example, the frequencies of the qubit modes, and they go through an extremum at exactly 0 or integer flux. So you tune it to that particular point.
Off, what would you even see? I mean,
So that's a good question. So it's actually not a problem. I sort of simplified the thing to, let me just go back to the Hamiltonian. There. Okay. So we have so far only worked at that particular point. But the sort of the theoretical analysis I presented you allows you to calculate what happens. So for example, this kind of terms to the lowest order will give you 3-body interaction terms, just like it does for 3-wave mixing for the amplifiers. But what you will get is sigma x, sigma x, sigma x between the 3 qubits, and that coupling will turn on as you turn up the flux.
But the RWA will tend to kill that.
Exactly. So unless those frequencies are in a particular ratio, or you're sending drives which give you the 3-wave mixing, they will not do anything to first order.
But would those drives give you some shortcuts around?
Exactly. So the other thing which I didn't really talk about is that the same techniques which you use for, because this gives you the parametric interaction, right? So you can think about the analogous amplification picture. So I guess this will be now mostly the Hattridge group will probably understand what I'm saying, but the 3-body mixing term gives you 2 kinds of processes. If you pump at the difference frequency, it allows you to do a swap. Basically, you do a what's called a noise-free photon conversion. In the quantum picture, it will basically give you effective dipolar coupling between those 2 modes. So you will create, even though you have 2 modes which are at different frequencies, so they will not normally, flop back and forth, but by doing a difference pumping, you will create an effective interaction. So you can flop back and forth between that. So that allows you to turn a coupling on of that type. If you do the sum pumping, which is what is used for the amplifier, that in this picture actually means that you can go from the ground state to the entangled state directly. So in the 2-qubit subspace, if you sort of ignore the 3rd qubit and treat that as the pump, because that's what happens, you're creating these entangled pairs. So you go from 0, 0 to 1, 1. So those kind of operations we have not tried yet, but that's something we will look into. So it might actually give you some shortcuts to do certain kinds of.
Because you might have some 3rd order stuff, especially once the broken symmetries in your new.
3rd order.
I mean, in your new one where there's the symmetry is broken.
Yes. So you don't. But the thing is, to the first of all, because you're only working in normal modes, you never get dipolar couplings.
Okay.
And
That's how you turn on the flux.
yeah. So that still works out. So we've actually done some measurements by moving away from the flux, and nothing too crazy goes on. Of course, you have the same problem that this as you go very close to a quarter flux quantum, and then the system becomes unstable, and then you can't bias there.
Okay, unless there are any more questions, let's thank our speaker.
Thank you.